website to get more information about it and also see other seminars that are happening. In addition, oh, I forgot, I did not paste the link I intended to. If you have ideas for projects at the intersection of AI and health, especially if you're a clinician looking for support from the machine learning side, we encourage you to fill out this survey that I pasted in the chat, and we will go over it and try to connect with you and connect you with a team as well to actually work on the problem. So with that, I'll hand it off to my co-chair, Professor Ying Ding, who will introduce our first speaker.
Great. It's our great pleasure to invite Steve Jiang. So Dr. Steve Jiang has a very rich experience in many places in the United States about the what is oncology, radiation oncology. So he got his Ph.D. at the Medical College of Ohio, then postdoc training at Stanford, then joined Mass General Hospital, Harvard Medical School as assistant professor of radiation oncology, then moved to UC, University of California, San Diego, and lead advanced radiology therapy technology there. Then he moved to UT Southwestern, and he built a big center with about the radiation oncology. So he's vice chair for digital health and AI of Radiation Oncology Department, Director of Medical Physics and Engineering Division. He's a fellow of Institute of Physics, American Association of Physics in Medicine, American Institute of Medical and Biological Engineering. Dr. Jiang's research covers cancer radiotherapy, and he has funding by federal, state, charitable industry funding for over $20 million, and very productive. So now it's a great opportunity for us to hear what his latest research. Thank you very much.
Well, thank you, Ying, for the kind introduction. Well, thank you for you both, Ying and Jiang, for giving me this opportunity to share our work with our colleagues in Austin. So, like Ying said, I'm a medical physicist working at UT Southwestern Radiation Oncology Department, and we've been focused on the clinical application of AI. And here today, I want to talk about some of our experience in that area. So this is our Maya lab, medical AI and automation lab, established about 80 years ago. It's a multiple PI lab. Our mission is to develop and deploy AI to solve real clinical problems and to improve patient care. We focus on the developing AI technologies that can directly impact clinical practice and translating AI innovations into the clinical solutions, right? So the lab mainly functions like a platform to facilitate AI research collaboration, clinical translation, education, and commercialization. It's mainly supported constantly by 10+ R1s and other grants. So a few example projects in my lab, like one is done by my colleagues David Xu and Jiang. So the standard radiotherapy for head and neck cancer is to treat the whole leg for certain stage of cancer patients in order not to miss the malignant nodes. So you can imagine the toxicity is quite bad there. So they developed a deep learning model to identify the malignant nodes out of benign appearing nodes. And therefore, you can focus radiation on those smaller area to reduce the toxicity. The good thing about this work is it was one of the earliest AI model validated by a prospective clinical trial, and then it be used for other trials and clinical practice. Another example is the personalized directives for radiotherapy treatment planning. So we found out there is a good correlation between patient's anatomy and the optimal radiation dose distribution. Then we developed a model to predict what is the optimal treatment for this patient. Then that gives you the individualized directives for treatment planning. We implement this work in the clinical practice about 5 years ago, and we have been using that for more than 1,000 patients now. It is being commercialized by companies through a separate new product award. Another example is an intelligent automatic treatment planning system. Treatment planning is a very important part of radiotherapy. Basically, a planner operates like a commercial planning system for like a day or even longer sometimes to come up with an individualized treatment strategy for patient, then present that to the attending physician. The physician will review the plan and give feedbacks, and then the planner will go back to improve it. So it's a iterative process that takes multiple days. At Maryland, we developed this a virtual planner, which can operate the planning system automatically, and a virtual physician, which can look at the plan and tell you, if it's good or bad, how to improve it, right? So this tool will be doing this iteratively. The model was trained with reinforcement learning, and then tested with this online planning challenge, ranked like number 3 among all the human planners. Another project is a real-time localization system. So basically, we use Bluetooth Low Energy, give every patient this tag, and also every equipment, every piece of treatment device in 2 clinical buildings where we have hundreds of Raspberry Pis embedded, hidden on top of the ceiling. So this project started about 10 years ago. Then we struggled for a year because the accuracy was not good, because Bluetooth Low Energy signal is quite noisy, not stable, inaccurate. So eventually we solved the problem with LSTM model. We have the developer carrying like multiple tags randomly walking in the buildings, and then we chop those trajectories into segments and then did a Monte Carlo simulation to simulate millions of different trajectories to train the model. So that's how we achieved 100% accuracy. So we implement that clinically in January 2019, and we developed about 18 clinical applications based on this technology. Like one example is this photo here at the bottom, right? In each treatment room, we have a touchpad. The therapist will have that when the patient walks into the vault. It will identify, which patient, and will pull the patient's information from the information oncology information systems, and then tell the therapist, everything is checked. This is the right patient at the right time with the right machine, and also pop up with like a to-do list, what you need to do for this particular patient. Another example is like during the COVID pandemic, we were still treating patients at our full capacity, and those patients cancer patients are old and typically old and vulnerable, right? So we were very careful in terms of screening for COVID, right? But we were still thinking that may not be enough. There were like quite some symptomatic patients, right? So we decided to develop an AI watchdog to locate, because for those patients, they all have like CT scans, right? So we have this watchdog running in the background, intercepting the images and look at COVID pneumonia. And if it found something suspicious, we'll send an email automatically to the clinical manager. And we implement that clinically in August 2021, and there were like 86 alerts triggered before Omicron. So I think it was about 6 months-ish there. The accuracy was 75%. So now you get a feeling, what kind of projects we're working on here. Very clinical, right? And then also we have been working on, overcoming the barriers for the clinical implementation of AI. So a student did this quick PubMed search, which tells you the research in AI in medicine has been growing exponentially, but it has not resulted in widespread clinical deployment yet. There is a large gap, translational gap. The reason for that is the current AI research is mostly focused on the model accuracy and external validation. Even for externally validated and accurate models, their translations to real world may still fail because there are many practical problems. Those are the common considerations, right? People talk about explainability, interpretability, ethical, legal issues, economics, outcome, education, all this kind of stuff, right? For us, we have been focusing on one big problem that we think is actually very critical. That is clinician buy-in, right? They don't want to use your AI tool because it's lack of rigorous prospective validation in real-world settings. It's from a research lab. It has a limited handling of clinical practice variations because you assume everyone is, your AI gives a standard solution. Everyone should just use it, right? It has a poor workflow integration. It does not help them actually end the work to their shooters. Also, they worry about, hey, you can replace me, So unclear accountability, liability, minimum incentives, cultural resistance, that's always there. So I will just focus on one of those problems. That's the variation in clinical practice. So medicine is still an art in many cases. Evidence-based medicine and clinical guidelines only give physicians the floor, not the ceiling. So they have a big room to exercise their own judgments. Therefore, there are variations in clinicians' clinical practice, right? It's not there's often no ground truth to tell them, which one is the best. That is an important reason for those variations. And then some variations are inherent, right? So we separate those clinical practice variations into two types. Type A stem from lack of experience, like between two physicians. If they treat the same patient differently, maybe one physician is way more experienced than the other. So that is more like that kind of variation is more like a data noise. Can be reduced with increased experience, enhanced training, and AI assistance. But type B reflects different practicing styles. If you can have two very senior physicians, both are very experienced, they may still treat the same patient differently, right? So due to the trade-offs, sometimes they consider different trade-offs, like Pareto optimization between things like tumor control and toxicity, right? So we think that kind of variation reprint signal should be respected when you're clinically deploying AI. And the trust between AI and physicians can be fostered if you recognize type B variations. If you not just say, hey, that's still noise, we should only give you the one standard, right? So the balance between standardization and personalization is important to implement AI clinically. I'll give you one example. This is like a post-operative post-cancer radiotherapy. So the prostate gland has been surgically removed, but there are still some residual tumor cells in the post-bed area, but those are not visible in clinical images, right? So this kind of segmentation, image segmentation problem is very different from the typical ones where you have an object to identify, which is defined by the variation of image intensities, right? Here you don't have that. You don't have a well-defined object. It's imaginary. So the current clinical practice is physicians manually delineate the target CTV, we call it CTV, clinical target volume, based on information like the relationship with the nearby organs, pathology reports, pre-op MRI, and other stuff, right? you can imagine there's a large variation among the physicians. Here, like the images shows like in our department, 4 GU radiation oncologists countering CTV for the same patient. You can see the large variation among 4 physicians working on the same disease site in the same group, right? We developed a deep learning-based segmentation model to auto-segment CTV. Then we did a observer study with experienced practicing physicians. We showed them in a randomized, blinded way. There is a clinical CTV contour, there is a AI CTV contour, and we showed them each of those physicians had like 30 cases, 30 patients. Half of those cases were their own patients treated more than a year ago. So that was their own work segmenting the CTV. The other half were from their colleagues in the same group, the other 3 physicians in the same group, right? We asked him to score the quality of the segmentation from 1 to 4, 4 being like a perfect, no need to change. 3 like with minor changes, 4 or 2 like major changes, 1 is like totally garbage. And then we also ask him to identify between the 2, which one you want to use clinically for your patient care. So we found out it's very interesting. They like their own work. They did not know it was their own work. They like their own work slightly more than AI, 3.4 versus 3.2. 60% of the time they choose their own contours for patient treatment. However, they like AI way more than their colleagues' work. So they gave 75% of the time they like AI contours more than their colleagues. So then we were thinking, is this consistent and learnable? So then we use their names, physicians' names as labels to train our classifier. We found that you can achieve 87% accuracy. Then we also look at the correlation with outcome toxicity, and there was no statistically significant correlation, so which is good. But then the problem is, what are you going to do now, right? There's a dilemma there. And the challenge is that they have multiple contouring styles, and there's no evidence showing one is better than others, right? There's no way you can convince them to, hey, let's just use the average or one style, right? Without hard evidence, you cannot convince them. And then if you offer them, if your model is trained with data from many physicians, you essentially give them like a average contour or from like a expert panel. That's then each time when they use it, they have to revise it to match their own style. That's frustrating and also inefficient. Eventually they'll give up, say, hey, I just do it myself. I don't need to use your AI tool, right? So your AI implementation will fail in that case. So our idea is, well, maybe we should develop an AI model that is style aware and adaptable, right? So the model provide personalized output to align with the physicians or institution style, right? And then you can also allow them to access other people's contours easily for learning and convergence purpose, right? So that might be a good balance between personalization and standardization. So then we trained a very simple model, ULET, one encoder but multiple decoders, each decoder corresponding to one physician style. Very simple model. But then for each physician, we'll offer their own style. Like if you look at the images on the right bottom, the red contour, that is like the physician's manual segmentation. The blue one is from like mixture data, model trained with a mixed data set. So that is different from the red one. The pink one is from this new model we call PSA-NAT that matches physician style very closely, right? So we came up with the idea, in general, this is not only this project is only about CTV segmentation, but in general, the variations in clinical practice are everywhere in medicine, right? In clinical medicine. So how to handle those things in general, right? The idea is train a model with the data you have, but when you deploy the model, I think you should adapt the model to the local clinical practice, right? And then when the clinicians use that model, by default, you should give them, what they want, their own style. However, with a very simple interface, like in segmentation problem with a mouse click, they can also say, hey, how my colleagues will handle this patient, or how this expert somewhere at Anderson will handle this patient, right? So they have that for reference when they don't feel very confident. It's at the fingertip, right? So by doing this, we think you can improve efficiency when they feel confident, but when they are not so confident, there's also an opportunity for them to learn and they eventually converge to best practice, right? So I'll talk about clinical deployment AI running out of time. The current practice is model-centric AI. We focus on the optimizing model architecture, accuracy, benchmark, solve one narrow task, and train on retrospective data sets, evaluate in narrow controlled settings, not real-world workflow, ignores workflow integration. And basically, that's why there's a translational gap because we focus too much on the model itself. So our proposal is to focus on a system-centric approach, shift focus from building a better model to building a working system. The system here I'm talking about is like compound agentic AI system. I think you guys are all familiar with that. All the benefits here and listed here. And also it develop the development as a continuous life cycle, right? Design, deploy, monitor, adapt. The goal is to develop safe, adaptive, clinically deployable AI ecosystems. The advantage is it addresses the real barriers to adoption, and we believe that's what we need. Compound agentic systems are what we need for real-world clinical implementation of AI. So we are working on such a system. Like here, you can see for each clinician, we want to develop a personalized AI assistant. And then there's a bunch of AI agents, each responsible for a specific clinical task. They work together as a panel of experts. And then there's an AI agent here, data collection, integration agent, retrieve in real time data from different clinic like data sources like EHR, PACS, OIS, that kind of stuff. And those data will be pre-indexed into a searchable index database, and AI agents will get data from there, from those vectorized database. And also agents can access different clinical tools, including other AI models, and also a large index database. One example is for auto-segmentation, which is beyond just an auto-segmentation AI model, right? During you need the deployment and adaptation agent when you deploy the model in a new clinical setting, right? You can do automatic acceptance testing, model commissioning, adaptation, right? Also, when you use it on patients, you can run the auto-segmentation model. It will review the output, assess the quality through like uncertainty quantification. Then you can suggest improvements, and then you refine the contours using maybe another AI model. It will do this iteratively until it achieves the clinical acceptable quality. And then there's another agent can monitor the model performance over time, right? Because the model looks good now, but 3 years later, it may not work during the clinical practice change, right? Data drift, that kind of stuff, right? So you need to monitor that and alert users for necessary model updates. So as you can see, even for a simple clinical task like image segmentation, one model is not enough. You need an agentic compound system, right? For decision-making seminar, a predictive AI model is not enough, right? You can have a clinical dashboard and a visualization agent to retrieve and process data from multiple sources, present the information in an intuitive format to the clinicians. They highlight, for example, in oncology, like tumor response trend, previous treatments, risk factors, that kind of stuff, right? And also you can, of course, predictive model is important here. You can run the model, and also you can retrieve for rare cases. You can retrieve similar cases previously treated here or somewhere else, right? Using that as a reference. And then you can have a panel of AI experts, like tumor board kind of thing, give you suggestions from different specialties. And then can also get the newest clinical guideline literature for you. So we developed like a clinical matching screening, clinical trial screening AI agent for each patient. Automatically found out which clinical trials or trial that may work for this patient, right? We have implemented this in 7 departments at UT Southwestern. Use it on like close to 4,000 patients now. Another example is a chatbot. So instead of opening up all kinds of clinical software database, you can talk to the chatbot, your AI assistant. The assistant will get information from in this case, oncology information systems. You can ask, what was the treatment history for this patient, right? Does this patient have a pacemaker? You don't have to find trying to go to Epic to find it out yourself. You can just talk to your assistant to get this information. So I'll stop it here. So basically, I'm trying to tell you, hopefully you agree with me that a single model does not work. You need a compound agentic system. Thank you. We have 1 minute for Chrissy.
Thanks very much. Any questions? I can ask a question and then we'll see if someone else does, but I think it's a really interesting example you gave with the variability. And I'm just curious, you sort of mentioned that there's